How's it going, everyone? Hope you're doing alright. Alright, today we're going to continue to go over questions on the review. If anyone has any particular problems you'd like to look at, let me know. Anything that y'all are interested in going over so far? Okay. Okay. So we're given a function, f of x equals negative 2x squared minus 3x plus 4. And we want to find f of x minus 2. So that means that if we plug that in, everywhere that x appears, which is here and here, both of those x's will replace with this binomial x minus 2. So we just take this equation, each x turns into this x minus 2 term. And because this one's squared, that means our binomial will be squared here also. Now, all we really need to do from here is multiply this out and simplify. We don't have to solve anything. We just want to simplify our expression and see what f of x minus 2 is equal to. Now, in order to kind of multiply everything out and simplify, we first have to square this binomial. So x minus 2 squared is x squared minus 4x plus 4. And if we distribute the negative 2 and if we distribute the negative 3, negative 2x squared plus 8x minus 8 minus 3x plus 6 and then plus 4. So we have a negative 2x squared, and then 8x minus 3x, so that'll be plus 5x. Negative 8 plus 6 plus 4, that will be plus 2. So that is our answer right there. A lot of students get to that and they think they need to keep going with it, but the instructions were only to evaluate the function at the given expression, and that's what we've done. We go through, we plug in our x minus 2, we multiply it out, we simplify it, that's all we have to do. Okay. Other questions? No other questions? Yeah. Both you zeroed in the same thing. Okay, number 4 there. We want to graph f of x equals log base 7 of x. Now, we think about it like this. We have y equals log base 7 of x. We convert that. This is y equals log base b of x. It becomes b to the y equals x. So 7 to the y equals x. Now, this is equivalent to log base 7 of x. So if we graph this, it's the same thing as graphing that. Now, the reason we chose to use this form, using the conversion formula, is that this one actually allows us to more easily plug in values for y and solve for x. Okay. So we start at the bottom. If we plug in y equals 2, 7 squared is 49. So 49 comma 2. Plug in y equals 1, 7 to the first power is 7. Plug in 0, 7 to the 0 power is 1. Plug in negative 1, 7 to the negative 1 power is 1 over 7. And plug in negative 2, 7 to the negative 2 power is 1 over 49. So when you raise it to the negative 2, it's like we have 7 squared, but the negative makes it a fraction, so it's 1 over 7 squared, 1 over 49. Okay. So we have 1 comma 0. It's right in the middle. 7 comma 1. 49 comma 2. It's going to be way out there. And down here, 1 over 7 comma negative 2. Or sorry, 1 over 7 comma negative 1. 1 over 49 times negative 2. Now, we know that we have a vertical asymptote right here on the axis. That hasn't been shifted over at all. But this graph appears very similar to other log functions, except because the base is 7, it's a little bit larger than some of the other ones we've looked at. It stretches more to the right over here, and it gets closer to the axis more quickly over here. It changes sort of changes the shape of the curve, but still goes through our point 1 comma 0, like any basic log graph does. Okay. Let's look at 6. I'll pick out one of these to work. This is 6b. Okay. Now the instructions here are to use the properties of logarithms to write each expression in terms of x, y, and z, with each variable of first degree. Basically, we want to separate this out into multiple logarithm terms, but we'll have a very simple term inside each logarithm, x, y, or z, it says. First thing we have is this division. When we have a logarithm with a division inside, we can turn it into log of the numerator minus log of the denominator. So, we still can keep going because we have different properties. These are multiplied together, and so whenever we have log of a product, we can make it log of the first one plus log of the second one. And actually the same thing applies here. We can get log of base A of 4 plus log base A of y plus log base A of z. Now the thing we have to be careful of here is that there is a minus sign in front of this logarithm, so that minus sign will have to apply to each of those three terms. There's one other thing that we can take care of, and that's the exponent. We have a third property that says if we have an exponent inside, we can factor that out as a coefficient. So this 2 comes outside and becomes a 2 times log base A of x, then a minus log base A of 4 minus log base A of y minus log base A of z. And that's now our expanded expression using those properties. So all four of those problems on number 6 are like that, where we just want to apply the properties to take the expression and expand it into a larger expression where each term is a little bit more simple inside the logarithms. Problem 7 is similar to that, except it has us go in the opposite direction. Let me just do A here. 4 times log base A x plus 2 times log base B of y. In this case, our goal is to... Oh, do you mean up here, Jared? The reason that these would be subtracted is because the division transfers into a subtraction, whereas multiplication becomes addition. Division becomes subtraction, multiplication becomes addition. So when we had multiplication here, we added those terms. This is multiplication here. We added each of these terms, although the minus had to be distributed. But the division that we originally started with, that turns into subtraction. Alright, this one is basically the opposite of the last problem, where we want to combine this into a single logarithm. And we start off with 2 or more logarithms in this type of problem generally. Now, before we can combine logarithms, they cannot have coefficients. So first step is take our coefficients move them inside as exponents. This is log base a of x to the fourth plus log base a, I don't know where it'll be, sorry, of y squared. Okay. Notice that we didn't change that in the last example until the very end. So that was the last one there. It's the first one here. Because now we're going with everything opposite. Because we just have log plus log, no coefficients. Now we can combine these because they're being added. And if they're added, that means we multiply x to the fourth times y squared to create our new expression. And so that'll be our answer there. The only thing that might be different in some of the other problems is that if there's a subtraction, that means we would divide instead. But here we multiply. Okay. Now for 8a, I believe this is one that we talked about in class at some point. This one utilizes what we call the change of base formula. Some of your calculators may actually be able to do this without changing the base, but in general we don't anticipate that they're able to. So our change of base formula says that log base b of x is equal to natural log of x divided by natural log of b. And instead of natural log, we could just say log of x over log of b. It actually doesn't matter which one we change it to, as long as both of these are changed to the same logarithm. Now the reason we would change it like this is that we can actually use our calculator to find the natural log of these terms and then divide. For instance, right here, whatever number is in the argument is on the numerator and the base is on the denominator. So we'll make this log of 15 over log of 4. And then we can go to our calculator and approximate that. Well, natural log, sorry. That's an old habit. When you get into advanced mathematics, you call it log, but you're actually talking about natural log. Anyway. So natural log 15 over natural log of 4, although it would have worked the way I wrote it anyway. Natural log 15 divided by natural log of 4. So we get a value of approximately 1.953. Notice if we had chosen to use log of 15 divided by log of 4, we get the same answer. So it actually doesn't matter which way we go as long as we're consistent. That's the main thing. Alright. problem 9, we have some equations to solve. Okay. Now, an equation like this, let me make sure. Okay. An equation like this, anytime we have more than one logarithm on one side of the equation, such as we have here, 2 logarithms, our first step should always be to combine those together, using the same properties that we just talked about in those earlier 2 problems. Because these are added, we know we multiply what's inside, so we get a single logarithm, but now we have x times x plus 5. And that equals log of 6 on the right. Now, at this point, there's 2 things that may happen. Either we have a logarithm equal to a logarithm, or we have a logarithm equal to a constant. So if there is no logarithm here on the right-hand side, that really changes our approach. And we'll talk about the other approach in a moment. But here, because we have log equals log, then since they both have the same logarithm, then what's inside must be equal to each other also. Now, essentially we cancel out all the logs here, although technically that's not exactly what happens. But again, we can only apply that if it's just 1 log on the left equals 1 log on the right. And what that leaves us with is an equation to solve. We can distribute our x, so that'll be x squared plus 5x equal to 6. And we'll subtract the 6 over, so it's equal to 0. This is factorable. We need to find 2 numbers that multiply to -6 and add to +5. Let's see, that turns out to be +6 and -1. Multiply to -6, add to -5. So it gives us x plus 6 and x minus 1 as our factors. So we get 2 solutions, x equals -6 and x equals +1. Now, for this type of problem, when we get 2 solutions, in general, we always want to check our answers for logarithms. Just be careful. There are certain situations that are more likely to create an incorrect solution than others. This is one of them. So especially want to check it here. Anytime we combine 2 logarithms together, we're in the danger of creating an invalid solution. So we try x equals -6. Now the reason that we know a particular value will be invalid is if we plug in the value for x and we end up taking log of 0 or log of a negative. log of 0 and log of a negative do not exist, and we can test that on our calculators. So if we plug in negative 6 here, we get log of negative 6. We can't take log of negative 6. It's not a valid operation. So we can just cross off negative 6 as an answer. It doesn't work. The other question is, well, does 1 work? Well, if we plug in x equals 1, we get log of 1. 1's a positive number, so that's a valid logarithm. 1 plus 6 is 6. Log of 6, that's a positive number, so it's a valid logarithm. So 1 is a good solution, and it is our only solution. Okay. Alright, let me do one more of those. I don't see one like it on your review, but it's one that we really like to ask in mathematics in general. It may or may not be something that you see in the final. Okay. Log of x plus 15 is equal to 2. Now again, we have two logarithms on the left-hand side. Step 1 is combine them. So we end up with log of x times x plus 15 equals 2. What is the base of this logarithm, since it's not written here? Well, it depends on the situation. Log with no base is actually base 10. And if we have Ln, the natural logarithm, then that's log of base e. So this is implied to be a 10. Well, we're going to need that, so let's go ahead and write down that 10. Because once we get to this point, we combine our two logarithms together. If we have log equal to a constant this time, we cannot cancel out the logarithms. Instead, we convert. Convert to exponential form. And again, our conversion formula says that if we have log base b of x equals y, that becomes b to the y equals x. And here's b, all that is x, and then here's y on the right hand side. And so making b to the y, that would be b10 to the y2 equals x, which is everything inside the logarithm here, x times x plus 15. Okay. Now 10 squared, we know that's 100. And we can distribute the x over here, so it's x squared plus 15x. Now, much like the previous example, we can pull our 10 over to, or 100 over to the right and set equal to 0, That way we can factor and solve for x. Okay. Now for our factor, again, we need two numbers that multiply to negative 100 and add up to a positive 15. And this so happens to be a positive 20 and a negative 5. So those multiply to negative 100 and they add up to 15. So we get 0 equals, and this will be x plus 20 and x minus 5. So that's going to give us, again, two solutions. X equals negative 20, x equals positive 5. And we need to check to make sure these are valid still, just like in the last example. Anytime we combine logarithms, there's a risk that our answer becomes invalid. So we check negative 20. We go back to the original equation. We plug in negative 20 here. Log of negative 20, that doesn't exist. We cannot take log of a negative number. So because we plug in negative 20 and we end up with log of a negative, we can say that, okay, that's not a valid solution. Let's check 5. Well, if we plug in x equals 5, we get log of 5, and 5 is positive, so that's a valid log operation. Plug in x equals 5, we get 5 plus 15 is 20. 20 is a positive number, so log of 20 is a valid log operation. So both of those work, so we can conclude that 5 is a valid answer. And so that's really the two scenarios that we run into there when we work with equations with logarithms. Either we end up with logarithm equals logarithm, in which case we can get rid of the logarithms, or we end up with a logarithm equal to just a plain number, in which case we have to use our conversion formula. In both cases, we have to check our answers. Okay. Do you have other questions on logarithms, or is that helpful right there? Okay, Brenda? Number 1? Did we not work that on Monday? It's been a long week, so I don't remember necessarily. Yeah, with the log functions, it seems like the amount of time that you'll spend on it compared to everything else was less, so definitely you can hope that there'll be a little bit less of it on the final as a result of that. Okay. Yeah, I think that'll, if you want to go back and look at the video on Monday, it's probably the first one that we did. Um, if you ended up joining a little bit late, you might have missed it, so, but it's there. Were there other questions? Did you all spend time going over the review in class yesterday with Mrs. Knisley? Okay, so tomorrow you're supposed to. Anything else you want to look at right now? Number 14, the log section. Okay. Right. Now, the key thing that we're looking at here are properties of logarithms. That's what we're looking at in this case. So key properties that they want us to use here. is that log base b of b to the x is equal to x. B raised to the log base b of x is equal to x. And we also have the addition, subtraction properties, and also the change of base formula in these 4 questions here. But these are the 2 I wanted to highlight. Let's look at the first 2 at least. For A, we want to determine if these are true or false. We have natural log of e is equal to 0. Now, natural log, remember, is log base e, and this is e to the first. Whenever we see e, that's e to the first. So according to this property, log base e of e to the first is equal to whatever is in this exponent, which is 1. So this one is false. Okay. B, we have x times log of 10 to the x equals x squared. Similar rule as what we just looked at here. We didn't really use that one at all. But when we say log with no base, this is log of base 10, and we have 10 to the x. Well, same rule. Log base b of b to the x is x. So log base 10 of 10 to the x, log base 10 and 10 cancel. So it's just x times x equals x squared, which is true. So now log base e and e cancel, and leaves us just the 1. Log base 10 and 10 cancel, so x is just left over. X times x is x squared. The part C and part D, or the third and the fourth one, however it's numbered, use properties that we've already talked about, but it's similar in execution. Other questions? You've asked about a lot of logs today. Don't forget that it's been a little bit longer since we looked at some of the earlier stuff, so it's going to be good to review those as well. Although this stuff, the logs, you're probably still trying to get a good idea of how to work those, which I understand. Any other questions? Number 2 on equations and matrices. Okay. I'll do A and then I'll pick one of the other three. Well, if you want to do one of the other three, I'll also do those, but I wanted to go ahead and start with A. Now, A here, it doesn't say to use matrices, so we have the option of using equations instead. And what this allows us to do is we can add these together. And notice that the 2x and the negative 2x are already opposites from each other. So we add these together and those cancel out. And negative 3y plus y is negative 2y. Negative 13 plus 7 is negative 6. And these cancel. Now, if nothing cancels, we don't want to add it together just yet. We need to multiply one or the other equation by a number so that something does cancel, and then we can solve for the other variable. This one's set up very nicely for us in that the x is already canceled out, so we can just solve for y by dividing by negative 2. And so we get y is equal to 3. So now we can take this result, plug it back in, and solve for x. So if we know that 2x minus 3y equals negative 13, 3 times y, 3 times 3 is 9, so 2x minus 9 is negative 13. Add the 9 over. So 2x is negative 4. And if we divide by 2, then we get x is negative 2. So, as far as how we write our solution here, you can either write x equals negative 2 and y equals 3, or we can also write it as an ordered pair. This ordered pair represents the intersection of point of intersection of these two lines if they were graphed in the xy plane. So if it's only two equations like that, with like just x and y, like we have here, we can go ahead and use system of equation methods to solve. We don't have to use matrices. You could go ahead and use matrices if you like, but we don't have to. Y'all want to see one of the other three, the three equation formulas? Let's go ahead and do B. It looks like might have some interesting stuff going on there. 2x plus y minus 2z equals -1. Three x minus 3y minus z equals 5. And x minus 2y plus 3z is equal to 6. Okay. First thing we want to do here is convert this into an augmented matrix. So for the x's, we have 2, 3, and 1. Our y coefficients are 1, -3, and -2. Our z coefficients are -2, -1, and 3. And our answers on the right, -1, 5, and 6. Okay. Now, first thing we always want to do with the matrix is get a 1 in the upper left-hand corner. Right here. There's a couple of ways that we could do that. If we took 2 minus 1, that would give us a 1. Or, more easily, we could just move this row up here and switch these two rows, and I'll put this 1 at the top left where it needs to be. So I'm going to take R1 and interchange it with R3, the two rows 1 and 3. We have 1, -2, 3, 6, 3, -3, -1, 5, and then 2, 1, -2, -1. Okay. So it gets our 1 where I want it. Now we want to take both of these and make them 0 using that 1. So we have 3 right here on row 2. So if we subtract this 1 3 times, we'll make that into a 0. 3 minus 3 will be 0. So we have to take row 2 and subtract row 1 3 times. Make that the new row 2. We'll also take row 3 and subtract row 1 twice. That'll give us 2 minus 2. To our 1. To R3. Now, in all of this, row 1 is unchanging, so we can just write that down again. Now for row 2, take 3 minus 3 times 1. 3 minus 3 is 0, as we intended. -3 minus 3 times -2. Minus 3 times -2 is positive 6, so -3 plus 6 give us a positive 3. -1 minus 3 times 3. -1 minus 9 is -10. And then 5 minus 3 times 6. 5 minus 18 is -13. We repeat that with row 3. When row 3 minus 2 times row 1. So 2 minus 2 times 1. 2 minus 2, 0, as we intended. 1 minus 2 times -2, 1 plus 4, that'll give us a 5. -2 minus 2 times 3, so -2 minus 6 is -8. Finally, the constant, -1 minus 2 times 6 Negative 1 minus 12 is negative 13. Alright, so our first column is taken care of. Now, next thing we want is to make this a 1. Okay, right in the middle. And to do that, we have to be a little bit more creative. You know, we can't just take 5 minus 3 or 3 minus 5. That's not going to give us a 1. What we could do is we can multiply this one by 2 and then subtract our 5. This times 2 is 6. Minus 5 would make that a 1. So we'll say 2 times row 2 minus row 3, replace row 2. Okay. The only row that we're changing here is 2. So we take 2 times 0 minus 0, 0. 2 times 3 is 6, minus 5 is 1. 2 times negative 10 is negative 20, minus a negative 8, so negative 20 plus 8 is negative 12. And 2 times negative 13 is negative 26, minus negative 13, so negative 26 plus 13, negative 13. Okay, now that we have a 1 here, we want to zero out these two terms above and below that middle one. So we can take row 1 and add row 2 twice. So I'll take negative 2 plus 2 times 1. Negative 2 plus 2 would make that a 0. And for row 3, we can subtract row 2 5 times. 5 minus 5 times 1, 5 minus 5 will make that a 0. Okay, so the only row we're not changing is row 2. Okay, so row 1 plus 2 row 2. 1 plus 2 times 0. 1 plus 0 is 1. Negative 2 plus 2 times 1. Negative 2 plus 2 is 0. 3 plus 2 times negative 12. 3 minus 24, negative 21. And 6 plus 2 times negative 13. 6 minus 26 is negative 20. Okay, row 3, we want R3 minus 5 times row 2. So 0 minus 5 times 0 is 0. 5 minus 5 times 1. 5 minus 5 gives us a 0. Negative 8 minus 5 times negative 12. Negative 8 plus 60 gives us 52. And in the last column, negative 13 minus 5 times negative 13. So negative 13 plus 65 gives us 52. Well, that's actually great, because right here, if we want to make this number into a 1 next, the only way that we have to proceed is to divide by whatever this number is. This works out really nice here because this is also the same number. So we're just going to take row 3 divided by 52 and make that the new row 3. So dividing those both by 52 just gives us a 1 for each of those. Now we want to make, we have 1s on the diagonal, now we want to make these two into zeros. Okay. And that should be our last step. Now, that's a 21. This is a negative 12. So for row 1, we need to add row 3 21 times to cancel out a negative 21. Okay. And for row 2, we need to add 1 12 times to cancel out a negative 12. So again, row 3, oops, that's a 3. Row 3 is the only one that we're leaving alone, so 0, 0, 1, and 1. Let's look at row 1. Row 1 plus 21 times row 3. 1 plus 21 times 0, 1 plus 0 is still 1. 0 plus 21 times 0, still 0. Negative 21 plus 21 times 1. Negative 21 plus 21 gives us a 0. And negative 20 right here plus 21 times 1. Negative 20 plus 21 gives us a 1. And let's look at row 2. Row 2 plus 12 times row 3. So 0 plus 12 times 0, 0. 1 plus 12 times 0 is 1 plus 0 is 1. Then here, negative 12 plus 12 times 1, negative 12 plus 12, 0. This left-hand side is exactly how we want it. 1's in the diagonal and 0's everywhere else. Let's just figure out this last number and we'll have everything. So we take negative 13 plus 12 times 1, negative 13 plus 12, and that is negative 1. So our conclusion is x is equal to 1, y equals negative 1, and z equals 1. Right, that's our process of Gauss-Jordan eliminations. It's actually the same steps each time. What changes is what depends on the numbers. Like, we won't always add 21 times row 3, but at this stage, it's however many times we need this one to cancel out this one. How many times we need to add this to cancel out that. Are there other questions? Well, this is our last meeting of the semester, so hope you all have gotten some use out of this course this semester, and that we've been able to explain business math a little bit more clearly to you with the additional time. That is the goal. Anyway, good luck on your final exams, whenever you end up taking those, Friday through Wednesday. Yeah, take care, enjoy the holidays, and hopefully we're back in classrooms next year. Everyone has a vaccine, and we're doing good. So that's what we have to look forward to, at least. So, normally we wouldn't have this class online, especially a class like this where it's split into two parts. It works so much better in the classroom. So we're able to break up into groups. We're able to give you worksheets more easily. We're able to do a lot of things more easily than we were able to do this semester. So I appreciate y'all working with us and being patient and somewhat eager to learn, as eager as we could be learning in a math class. I understand that the desire is not always there, but I mean, you all have a goal you're working towards, so I think that's good. Anyway, we'll end it there. So if you do have any questions, you're welcome to email me still on the review or whatever. Yeah, absolutely. Yeah, I'm ready for a break, let me tell you. I imagine all of you are as well. But yeah, hope you all had a good time, got some work done, and passed this class. So good luck with it. Y'all take care, and feel free to look me up for a class again under maybe a little bit better circumstances. So anyway, y'all take it easy. Bye.